started. Thank you so much for coming to the First Friday Colloquia, although this is actually a rescheduled First Friday, last Monday. For the Training Center for Early Childhood Research and Policy. My name is Jessica Logan. I'm a research scientist at the Training Center. And I am very excited to introduce Dr. Battista today, who is a professor in mathematics education here at Ohio State University. His major research interest, as I understand, is in student learning in math, and with a focus specifically in geometry and in geometric measurement. He's also really interested in the use of technology by teachers in mathematics education. His current project we're going to hear about today is looking at elementary school mathematics teaching with education, with technology, that was the word I was looking for, development and instructional use, and we're excited to hear from you. Thank you.
Thank you. Okay, so it's hard for me to imagine talking about learning progressions and squeezing it into 45 minutes, but I've tried. I've been really working on learning progressions for over 25 years, although they weren't really called learning progressions early on. And I think it's as you work with learning progressions, there are learning progressions that you develop for other researchers, okay? And then you can sort of rewrite those learning progressions so that teachers can understand them, and then you can try to integrate those learning progressions in curriculum for students. And basically, I've been involved in all three of those. So these are sort of curricula for students. This is a series of books that came out about a year ago that's written for teachers and helps them use learning progressions in teaching students in elementary school mathematics. And then this is my current project, and all of this was supported by the National Science Foundation. But in this particular, it's a computer-based geometry curriculum for grades 3 through 8, and it incorporates learning progressions into its branching and linking. In a sense, it's an attempt to try to make learning progression-based teaching available to all students, not just those who have master teachers who can handle this kind of thing. Okay, so what I'm going to try to do is I'm going to talk about what are learning progressions, why use them, instructional use of learning progressions, and also something about using them with teachers. So here's just my definition of learning progressions, which is not that different than many people. So learning progressions are descriptions of the successfully more sophisticated ways of thinking about a topic that follow one another as students learn about and investigate the topic. And for me, thinking is conceptualizing, reasoning, procedure, strategy, implementing, okay? Okay, so, and all the learning progressions that I'm talking about are empirically based. Okay, they're not somebody sat in an office and decided this is logically how things should go. So I think all the learning progressions I'm talking about were empirically determined. Okay, so why use learning progressions? The research foundations, basically it's sort of built on this idea that students construct meaning based on their current meanings, okay? And so if we're going to teach students in maximally effective way, we have to figure out where are they in their reasoning and their conceptualizing, and how can we build on that in instruction. So that's sort of like the theoretical, like 10-second theoretical framework. But I think the other part of this for me is that if you look at all the research done in mathematics education over the last 30 years, I would say that the strongest finding is this, that instruction that is based on and continuously adjusts to the personal meaning students are constructing for specific mathematical topics improves student learning, okay? So there's a number of related concepts that I thought I would talk about, and these will make some issues I suspect pop up. But learning progressions are not developmentally inevitable, okay? They're not like Piaget stages. Learning progressions always depend to some extent on instruction, okay? A level of sophistication, which is basically the concept I used before people decided to call it learning progression, is a distinct type of cognition that occurs within a hierarchy of cognition levels. So for me, that's level of sophistication. Some researchers are viewing levels in a learning progression sort of like Doug Clements and I did many years ago, that in some sense it's sort of like a configuration of problem-solving strategies that has certain activation weights, okay? Somehow I don't think that adequately captures how I think of students at a level, but it is certainly a way that people think about it. So for me, an ordered set of levels of sophistication is basically a learning progression, and I sort of view them like this. There's these cognitive plateaus that students have to move through, okay? And I think that there's a lot of people talking about learning progressions, and sort of the grain of the learning progressions differs widely. For instance, in science education, often the grain is very wide, okay? Whereas in math education, it's narrower. But for me, I think I think one of the big problems we have in teaching students mathematics is students at this level, you want them to get them to the next level, and you can't figure out how to do that, okay? I think about my early teaching career, and I think about my failures at times. I mean, the successes I don't remember so much, but I do remember some of the students I failed with. And I can remember certain students that I kept explaining and explaining and explaining the idea, and they just never could get it. And now I know why, but I didn't understand then. So in some sense, I think that the kind of learning progressions I try to come up with are ones where the jumps are reasonable for students. And for me, reasonable means within a day or two, working intensively with the student, I probably can get them to make that jump, okay? So you have to get vacation pictures in your presentations. But in many ways, I sort of think of, it's the next picture, I sort of think about when I went rock climbing with my son, and he was in junior high, and he didn't have much experience climbing. And we were sort of climbing up. It wasn't this particular one, that's a little too steep for him. But it was actually sort of easy for me to figure out where the footholds were, and where I should step next, and where I should put my hands. But it was very difficult for him. So I could try to help him with that. I could try to point out the footholds. But ultimately, it was him. He had to pull himself up. And I think that's exactly what happens with students in learning mathematics. You can sort of help them see the footholds, but ultimately, you can't force them to move up. They have to do it themselves. So, another term that's out that's similar is learning trajectory. And for some people, learning trajectories mean the same thing as learning progressions. But for other people, there's a difference. So Les Steffi talked about an actual learning trajectory for a student. So a model of children's initial concepts and operations. It accounted the observable changes in these concepts and operations as a result of children's interactive mathematical activity in situations of learning. So it's basically trace out everything that you do with the student. And if you've ever read any of Les Steffi's stuff, you know that's exactly what he does. Doug Clements and Julie Sarama talked about learning trajectories as descriptions of children's thinking and learning in a specific mathematical domain and a related conjectured route through instructional tasks, okay? So both Steffi's and Clements and Sarama were sort of talking about progressions through pretty much specified instructional treatments. Okay, for me, learning progressions are more general than that. They're not tied to a specific curriculum. So for me, the simple definition of learning trajectory is an instruction-dependent path through a learning progression. Okay, so you can sort of see my picture of learning trajectories for two different students. So I don't think that all students necessarily go through the exact same sequence. Sometimes students jump through or jump past. And you can also think about a learning trajectory as like this hypothesized route that you're going to try to engender in instruction. So why use learning progressions? That's the big question. So for me, it's pretty simple. Once I know where the students are in the learning progression, I know what to do with them instructionally. In the work I did with teachers, once we identified where students were, I knew exactly what to do, and they said, we have no idea. So that's why I spent a lot of time sort of working with teachers, trying to figure out what do they need in order to use learning progressions. Okay, so I want to give you just a quick kind of a couple of examples, okay? So here's a learning progression for addition and subtraction, okay? And I'm going to zoom in on just one part of it, okay? And so we're just going to talk about those three different ways of adding numbers, okay? So the count all strategy, a student might count 1, 2, 3, 4, 5 without raising fingers, then 6, 7, 8 while raising 3 fingers, okay? Count on, a student might say 5, then count on 3 additional numbers, 6, 7, 8, okay? So counts on from, all right? And then a derived fact might be, I know 3 plus 3 because it's a double, so add 2 more, okay? So those are the three strategies. And you can see Tom Carpenter and colleagues sort of trace students for the first 3 years of school in a particular curriculum. And you can sort of see how things progressed, okay? And it's important when the number facts really is memorization of a fact and a derived fact. So they lump those together. Okay, so we have these levels. So the first step in using learning progressions is determine where students are, what level, all right? So in some sense, individual interviews are always best, but teachers always ask, well, how else can we deal with this? So I'm going to give you an example of what one teacher did. She spent a lot of time with her students, first graders, talking about not only getting them to talk about their strategies, but talking to them about how they would write their strategies down on a sheet of paper, okay? I think she got more information from her first graders than many 4th and 5th grade teachers get when they don't say anything other than just tell me what you were doing, okay? So she spent a lot of time with students on that. So here's some of the stuff that her students wrote, and here, probably familiar with this kind of stuff. Okay, so I counted in my head 4, 5, 6, 7, okay? So the important thing to sort of recognize here is, can we figure out the strategy and map it to the learning progression? I counted by ones and basically counted all, right? I thought a little bit. I counted like 1, 2, 3, 4, 5, 6, 7. I mean, it's really interesting, the spelling that kids use. There are times, I think, that I had to ask my wife, who taught at that level for a number of years. And the numerals, obviously, are not exactly what you would expect. It's important here is she had this, I'm not going to show you all the students, what all the students wrote, but I think it's important to recognize that there were a few students in her class that she knew couldn't write their strategies, okay? So she would intentionally go over to them, ask, how did you do it? And then she would write on the student sheet, okay? I started at 8, 7, 6, 5. Okay, so you get the idea. So now, let's sort of map what the student said to like a chart for the whole class, okay? So we have a whole bunch of students who are counting all, and we have a bunch of students who are counting on or down. And so what I'm suggesting is, in a learning progression-based instructional approach, those two groups of students need very different kinds of instruction, okay? So I thought I should illustrate what that might look like. So for the students, so we want to get students from counting all to counting on. There are some sub-skills, which I've listed here, all right? Students can correctly produce a sequence of counting words beginning at an arbitrary number. They don't have to start at 1. And they have to know that if I count a set of objects and the last number I say is 7, that the number of objects is 7. Okay, for a lot of students, young children, it's like you say count and they just start saying numbers, okay? But it's not really related to the cardinality of the set. Okay, so moving from counting all to counting on. So one way we might do this, help students, is with this task. So show 5 squares in the configuration below and ask how many squares there are. Then cover the 5 squares, okay? And write 5 below it, and then put 3 more squares and say how many squares in all, okay? So the idea is, can you get the student to sort of not start at 1, okay? And it turns out that it's actually more effective to not start with the task that looks just like this and just say there are 5 squares underneath. For a lot of children, they have to see them, then you cover them, and then they believe that there are 5 under there. In fact, they can visualize them. I mean, if you sit with children doing this, you can see them. They'll actually count in the same configuration that they saw the squares. Okay? At some point, with some repetition, and especially if you keep starting with 5, do they get, I don't have to count 1 through 5. I can just start with 5. And we can sort of push that, okay? So that's the students moving counting all to counting on. How about students that you want to get to derive facts, okay? So one of the fairly effective ways to getting students to develop this kind of reasoning is with what people call quick images, okay? So I'm going to show you a picture of some dots for 3 seconds, then I'll hide the picture. I'd like you to tell me how many dots there are. Okay, so did you? 10, okay. All right, so there's 10 dots. Now I'm going to do the task again. 8, right? Okay. But how many of you counted 8? You didn't count 8, right? Okay. You sort of, the strategy is the whole is 10 and you took 2 away. Okay? Here's one more. Okay. So what's the strategy that students use on that? Well, basically, they sort of envision moving these 2 over here. That's 10, and then 4 more. Okay? There's a common kind of strategy with young students is to say something like 8 plus 6. Well, I take 2 from the 6, put it with the 8, that's 10, and then 4 more. Okay? And it's just the quick images sort of try to build those kind of mental models in students. All right? So I guess the moral of the story is, at least from my perspective, is that the students at level 1.1 need very different kinds of instruction than the students at level 1.2. And this teacher, in fact, did sort of teach in that way. I mean, she would group students, not every day, but maybe 2 or 3 days a week or something like that. Okay?
It'll be so much easier to do it now.
Okay.
Let's say you have students who went for the more complex place on the progression, would they generalize downward and get 1.2 along the way?
Oh, probably not.
Okay.
Yeah, I mean, it's not clear. I mean, I think in general that what happens with the learning progressions is if you try to skip a step, if you, as the teacher, try to skip it, you lose some students. Some of the students can't make the jump, and so they're not as successful, okay? Now, that doesn't, I mean, some students, I think, might go through from one level to the next really fast, especially like if you're working with gifted kids. I mean, they can move up really fast sometimes. And sometimes students will move up just by hearing another student tell about their strategy, okay? But in the kind of classrooms that I envision, if I listen to Susie and she comes up with the strategy, then I have to decide, do I want to use it or do I not want to use it? If the teacher shows me a strategy, I have to decide, do I want to use it or not use it? As soon as we get into you must use, then what happens is the student's sense making starts to fade, okay? And that's what we're trying to avoid. Okay, how much time do we have? Thanks. Well, to skip ahead quickly. So one of the issues that people have with learning progression sometimes is, are students at levels? Should we talk about a level 1 student? And my answer to that is generally no. I mean, I'm interested in what kind of reasoning is the student using at this point in time, okay? And usually, just saying the student is at level 3 isn't completely accurate. I mean, sometimes that happens, but students are constantly in transition. So it's a little too, it's oversimplified to say a student is. And I also don't like the idea of classifying a student. I like to think about the student's reasoning, because that's what I can build on, not, oh, this is a level 1 student. Okay, so how do you deal with that? Well, one way we've dealt with it, and so that I can get into some additional stuff, is thinking about profiles, okay? A CBA learning progression profile. So here's another learning progression. This is for place value. And here's a student in grade 2, and I'm not going to show you all his work, okay? But I'll show you just a little bit. So Mary has 24 cookies. She eats 6 of them. How many cookies are left? 24 subtract 6, 24, and he counts down, okay? But he misses a number, 20, okay? So in the learning progression, he's still having some difficulties with counting. Now, of course, this is counting backwards or down, not counting up, which the two are, you get one before the other. Here's another problem. Here he used an algorithm. So he said it was 11, so I put a 1 right here under 4 in 24, and a 1 up here above 4 in 47, and then I put 1 plus 4 plus 2, and it equals 7. What does this 1 stand for? To add with the 4 and the 2. Is it just a 1? Yes. Okay. So for us, that's an indicator that he doesn't really get place value in the algorithms. The students who did get it would say, no, it's a 1, it really is a 10. Okay? So he's sort of level 1. Okay? And I probably should mention that if a student can use an algorithm to do something, it doesn't tell you a whole lot about their conceptual development. So we always try to go beyond that. So here's another problem, but now he's using base 10 blocks, okay? I've got 36 and 28, base 10 blocks, okay? And he puts 3 10s in one hand and 2 10s in the other. 30, 40, 50, and then he touches ones, 51, and he counts on, okay? So he's actually jumped up to level 2, all right, with the base 10 blocks. On this problem, where he has pictorial kind of material to operate on, he's still at level 2. So the profile, I mean, there's a whole bunch of tasks, and we sort of keep track of that. But the profile is actually basically this. With no perceptual material, he operates basically at level 1. With perceptual material, he jumps up to level 2. Okay? So that actually helps us think about what does he need. And I'm not going to, I think I have more to say about it, but I won't, just to get on. But basically, we have to sort of build on what he is doing with the pictorial material and get him to be able to internalize that, okay? And so there's specific instructional techniques that you can use to get the student to sort of internalize that imagery. Okay, so the first two examples were primary grades. Now I'm going to jump up a little bit just to give you a good example of what happens when teaching ignores learning progressions, or the learning progression isn't sophisticated enough. Okay, so here's one learning progression for shapes. Okay, it's been around for 30, 40 years, something like that. And here is an elaborated learning progression. So certain parts of it were expanded, and basically I expanded it using some fairly long-term teaching experiments where we watch students every day. Okay, so what happens when teaching is inconsistent with learning progression? So here's an example. So one is sort of quantitative, all right? So Sharon Senk found that students who start high school geometry at Van Hill level 0 have little chance of learning to write proofs. Students at level 1 have less than a 1 in 3 chance, and students at level 2 have a 50-50 chance, okay? So, you know, you get students to level 2 and they only have a 50% chance of succeeding in high school geometry. That's not really, that's not my vision of a successful approach to this. At the end of the school year, 4%, 13%, 22% of students at levels 0, 1, and 2, but 57, 85, and 100% at levels 3, 4, and 5 were mastered proofs. So these levels, Van Hill levels, were the ones at the end of the year, and those were the ones at the beginning of the year. Okay, so we've known for a long time we have this huge problem in mathematics, high school mathematics. Students don't do well in high school geometry. At one point, it was the most hated course of all courses in high school. The proof-oriented, I mean, you know, you just talk to somebody, they say, oh, I remember proofs, and then they frown. Okay, so here's a slightly different assessment, but fairly recent, I don't know, 10 years ago. So here's a problem that tends to distinguish pretty well between students at level 1 and students at level 2, okay? So you look at those two shapes, it looks like you have a rectangle and a square, but if you look at the measurements, that's not the case, okay? And in a fairly good school district, only 22% answered that item correct. And to me, even more distressing is that the students at the end of high school geometry in 8th grade. So this is basically the upper 5% of students, okay, in this particular school district. Only about half of them got the problem correct. And there's no doubt in my mind that they had the capability to think about this correctly. Okay, so that's the quantitative. Now I want to show you the sort of the qualitative, which to me really helps to understand what's going on. So here's our task, and we have a teacher sitting with a student who has completed high school geometry, okay? So she looks at those two shapes, and she says her choice is A. It's a rectangle and a square, okay? And the teacher says, I'm curious about how you knew that A is a rectangle, B is a square. Well, the student, well, I mean, it's pretty obvious. You can just tell by looking. So you didn't need to use these numbers they gave you at all? I guess I could have, but I didn't think I had to. I mean, you can just tell by looking. It wasn't so obvious, then yeah, I'd look at the numbers. So you get this idea. I mean, that's a classic level 1 response to this task. Remember, this student has been through high school geometry. So let's go a little bit farther. So the teacher asked the student, how do you know if a shape is a parallelogram? I think it's just four sides and a set of parallel lines. Okay, how do you know if a shape is a square? All the sides are equal in a square and parallel. Oh, and the angles have to be 90. And what about a rectangle? And she gives her description. So she sort of jumped up in level on prompting, okay? So what does learning progression consistent instruction look like? So the teacher comes back to a similar task and says, the student says that's a square. And then the teacher says, well, what is a square and what is a rectangle? Can you define them? So the idea the teacher has in mind, look at the definition, compare what I see to what I've defined, and that should help the student move forward, okay? And then the teacher does some other good stuff that's consistent with the learning progression, because what he does is he sort of looks at the definitions and he tries to get the student to clarify, what do you mean by those definitions? So pointing to two neighboring sides in the figure, are these two sides parallel? Because remember, the student said for a rectangle, for a parallelogram, for a square, all sides are parallel, okay? It's not what the student really meant, okay? So, but you said in a square, all sides are parallel. Well, I meant the ones across from each other, like these two would be parallel. Do you want to change your definition? And so the student clarified, okay? How about the rectangle? Same idea. And then for the rectangle, you wrote the two sides are the same and the other two sides are equal. Do you want to specify which sides you're talking about? And then the student clarifies, okay? Okay, so now, using this information, look at this picture again. What is the shape? I don't know. It looks like a square. These definitions are right? I guess rectangle because the sides are different, but it looks like a square. Yeah, it's a rectangle. Not real enthused about the classification. Okay, so now that the teacher is getting into where I think it's learning progression, inconsistent instruction. Okay, and I want you to go back to what you said about there possibly being a rule about squares and rectangles. So you have to think about, what did the teacher just think, okay? The student agreed that according to the definition, that thing that she saw was a rectangle, okay? So, you know, the teacher might think, I got the student to say the right thing. I'm ready to push him farther. And the learning progression approach would be, no, you just don't know enough to know. You should go forward. Okay, so, and at some point, you know, the students always sort of, when they're sitting with somebody who seems to know something about geometry, so many students will say something like, oh, you know, is it all squares are rectangles or all rectangles are squares? I remembered we talked about that, but they haven't the slightest idea which is right or how to figure it out. So they had talked about this before, and the student through high school geometry still didn't know what was what. Okay, I want to go back, and you said that about there possibly being a rule about squares and rectangles, okay? Based on your definitions, can you decide whether there might be one? I don't know, I can't remember. Draws a square and labels each corner 90 degrees and each side length 5. Okay, let's go through your definition of a square and test this. And then go through the definition of rectangle, test this. So the student says, for rectangle, the sides across from each other are the same, but they're all the same. So can it still be a rectangle if they're all the same? Yeah, that's what it is. That's what I was trying to think of yesterday. So a square, I mean, a square is a square and it's a rectangle. Like this is also a rectangle because it fits the rules. So the teacher got the student to say the right thing. Okay, so then the teacher comes back to this. And the teacher writes, as a definition of rectangle, a quadrilateral with 4 angles equal to 90 degrees. Okay, now, The difference between the teacher's definition and the students is the students listed all the properties, which is sort of level 2 kind of reasoning. The teacher lists just one sufficient property, which is level 3 kind of, it's later level 3 kind of reasoning. So, what's the student think about this? Is this right, or am I supposed to tell you why it's wrong? Well, do you think it's wrong? I mean, I guess probably all this stuff is true, but like for the rectangle, you don't say anything about parallel or equal sides or anything. You don't say anything about the sides, so it wouldn't be the definition, okay? Level 2.3 response. And then they keep talking. So the teacher is talking about, are all parallelograms trapezoids? No, why not? Well, because then they would be called trapezoids and not parallelograms. But what about squares and rectangles? Remember, you said that all squares are rectangles. Yeah, I guess, but I don't really see how that makes any sense either. So, it's in my mind, this is a clear example of a teacher trying to push a student to a higher level before the student is ready. I mean, I would have never tried to push the student into level 3. I would have done a whole bunch more at level 2.3. Trying to make sure they really understand the properties. And then there's sort of steps up to get to, I mean, the teacher's really trying to get the students up to 3.3 or 3.4, and the student was sort of operating at 2.2, 2.3. It's just too big a jump. The student can't make it. And whenever you put students in that situation, they start to abandon personal sense making. And to me, that eventually means they're going to end up failing in mathematics. I mean, it happens to people at various places. Second grade, 6th grade, I've seen it happen like junior year in college as a math major. All of a sudden, it just starts to unravel. Okay, so just back to the picture we had before. So, we don't have too much time, but I'll try to say a little bit about the cognition-based assessment and teaching project. Basically a 10-year project with NSF support. And in the first phase, I developed assessment tasks, learning progressions, and instructional tasks for elementary school mathematics. And in the second phase, I basically investigated how elementary school teachers would use these learning progressions. I was supposed to say something about how do you construct learning progressions, which is, that's a whole topic in itself. But basically, we started with what the research said. We tried to consolidate what the research said. We tried to derive some initial levels based on what the research said. And then we just spent 4 or 5 years just testing students, giving them assessment tasks. Like for place value, we probably gave 50 to 60 different tasks over a 5-year period, okay? A lot of learning progressions are actually developed based on just giving 2 or 3 tasks. And so we found that if you just looked at that, you didn't get a big picture of, you know, suppose you're looking at all the possible tasks, okay? So I'm gonna skip that. So the first phase, developing, and that's basically it's interesting that these books came out just recently, but at the end of the 10 years. Okay? The first 5 years, I pretty much had figured out where are students in these learning progressions, what do they look like, okay? But then I spent another 5 years talking to teachers to try to figure out how should we write these? How should we illustrate these so that the teachers could use them? For instance, I told you that when I know where a student is in a learning progression, I know exactly what to do with the student instructionally. The teachers told me, we don't know what to do, okay? You need to help us. You need to say, if a student is at this level, what do I do? And these were good teachers, okay? I mean, I enlisted teachers who I thought really knew what was going on. So I think that, you know, when they told me things, I paid a whole lot of attention to what they said. So I actually went beyond geometry in this particular project into number. It's probably worth me just saying a minute about, what did we put in these books. So first you have to identify what the core mathematical ideas and processes are. So place value, okay, that's a core idea in elementary school mathematics. Core reasoning processes sometimes aren't so familiar. So iteration, like in skip counting, or in, like if you want to find the volume of a box, you find out how many in a layer and you iterate that. I mean, iteration occurs everywhere. The distributive property actually occurs all over elementary school mathematics. Then we provided these research-based learning progressions and sets of tasks that would help teachers figure out where their students were. And then, really important, examples of students reasoning at each level for each task that they gave. And then it's suggested instructional activities. Okay, so with the teachers, basically, 2 minutes? Okay. Basically, we followed the teachers for 1 to 5 years. Originally, I was going to get one set of teachers, work with them a year, then get another set, work with them a year. And the first set of teachers wouldn't quit. I mean, they just wanted to keep going, okay? So it's an interesting progression from teachers who were skeptics at the very beginning. I could think of one teacher, to a teacher who, at the end, years 4 and 5, was teaching other teachers how to use the learning progressions. We had teachers basically doing things at all 3 tiers in the RGI levels, okay? What did some of the things the teachers say? In some cases, I gave my students credit for knowing more than they actually did, which hampered my instruction. In other cases, I gave them less credit for knowing what they did. Knowing exactly where students are in mathematics isn't such an easy task. I had one teacher, and again, a good teacher, pick the person for her teaching experiment with a student that I required all of the teachers to do. She picked the student that she thought was best in mathematics and the student that she thought was worst. And after the interviews, she switched. And the one that she thought was the worst just wasn't very articulate, but had really good thinking. The one that she thought was best was really good at saying the few things that she knew. So, well, there's lots of other stuff, but in the interest of time, let me just say these few things. So, helping teachers understand learning progressions. What are the difficulties? One, the amount of information in learning progressions. It's fairly complicated, okay? That's an obstacle. 2 is there's not only mathematics you have to understand, but there's psychological complexity to students' thinking. 3 is time management. How do I, once I get what these levels look like, how do I integrate it into my curriculum to make it useful? And basically, the teachers resolved these issues in year 1. It took at least 2 years, okay? Year 1, just figure out what the levels were, okay? And feel comfortable with them. Year 2, sort of revise their curriculum and sort of figure out, okay, in this unit, I'm going to do this from CBA. In this unit, I'm going to do this from CBA. And so they had a plan, and then they implemented that plan. Okay, I think I'll stop with Teacher 13. I mean, I have a lot more to say, but I thought I would open it up to questions.
We want to know about Teacher 13.
Oh, okay.
What does Teacher 13 say?
All right, okay. So this is just an example of learning the levels. So, so I asked her in year 1, how important is it for you to determine exact CBA levels for students? It could be, but it's not right now. I'm still trying to get my head around and think about, do I want to group these children in math groups? But I don't know if I want to do that yet. I think it could be very useful and very important, but I don't know how I'd work it, so I'm scared to try, okay? Year 2, she just blew me away when I walked into her classroom. She said, I have 18 kids in my classroom. I have 1 that's at level 0. I have probably 4 that are at level 1.1, independently and always. Probably 10 of my students are at 1.2 independently, but they probably will go back and forth depending on how hard the problem is. And then I probably have an extraneous 3, they're at 2.1, and then I have 1 that's at level 4.2, and I think that covers it. And she didn't look at any notes. She just actually knew where all her students were, okay? So it's just this huge change from not even sure that she wanted to use this stuff till this is the first grade teacher that I showed you the written work. And she did group at times. Another teacher basically totally integrated cognition-based assessment into his teaching, and he teamed with another CBA teacher, and so they actually integrated some of the CBA assessment tasks into their grade level tasks for their school district. And so they actually could screen students, and they worked in they called it a quad. So there's 4 teachers would work with like 4 classes, but they grouped the kids based on that. And generally the CBA teachers would take the students who were struggling and try to move them forward. Probably the greatest success story that I can think of for CBA is teacher 19, who was a 3rd grade teacher. And at the beginning of the year, one of his students, he said, was at the kindergarten level. He started working with that student with CBA, and by mid-year, he said, she's at 3rd grade now. So she actually fits in to the rest of the class.